Okay, doing something a little bit different today. We've got a problem here from the Vienna Integration Bee 2024, problem number 24. We have the integral from 0 to 1 of arctan of x over x plus 1 dx. And before I get started, I just want to thank Alperen for providing me with a list of problems. There's a lot of good problems on this, a lot of variety. Okay, so to get started with this, the first thing I notice, we wish this was an x squared right here, right? Because think about how easy that would be to do a u substitution. But clearly that's not the case, so what we can do a lot of times when we have arctan is set up integration by parts, and we'll do that using the DI method. Coming over here to the right, we'll set up our DI table for tabular integration. We want to differentiate arctan just because we don't really know how to integrate that. And then 1 over x plus 1, that's going to be easy to integrate. First, the derivative of arctan, that's just going to be 1 over x squared plus 1. And over here, integral this is just going to be natural log absolute value x plus 1. I think I can drop the absolute value here just because x is between 0 and 1. So that means that this thing here, this is always going to be positive. So let me just put parentheses in so we don't let that bother us. So then we have part of the solution here on the diagonal. Let's just put that down. We're going to have arctan of x natural log x plus 1. And we just need to evaluate that from 0 to 1. This piece is going to be an integral. So this is going to be, for an integral, let's put this together as natural log x plus 1 over x squared plus 1. See, we got the x squared that we wanted here, but now we don't have the arctan, so I don't know what's happening. Now from here, we can go ahead and just evaluate this, but this still looks like a problem, so it's not like this really solved that much for us. It just gave us another problematic integral, but at least we can take care of this part. So evaluating this up here, first we want to plug in a 1. Arctan of 1 is going to be pi over 4. Then plugging a 1 in here, we end up with just natural log of 2. Then for the second part, when we plug in a 0, arctan of 0 is just 0. Then for the next part, we're going to have natural log of 1. Natural log of 1, that's also 0, so this part goes away. And so this first part is just going to be this right here. So I think I'll just grab this and clean up the board, and we can focus on this integral right here. Okay, now continuing with this integral here, I've just brought it down here and put a label on it of I. And going ahead, what I want to try on this, noticing we have x squared plus 1 in the denominator, we can do trig substitution on this. Even though we have natural log, it's still going to help us simplify this. So what I'll do is, for this trig substitution, I'll set x equal to tan of t. That means from that, isolating the t, we're going to have t equals arctan of x. Then I'll take a derivative. So for the dx value, we find secant squared t dt. So then coming over here, first, let's update the bounds on this. So plugging 1 in here, arctan of 1 is just pi over 4. And then plugging in 0, arctan at 0 is just 0. Then for the numerator, we end up with natural log tan t plus 1. And here for the denominator, this is going to become tan squared t plus 1, but we have this dx here, which is going to be secant squared t dt. But for this right here, we can use the identity that this is the same thing as secant squared t. And then I was almost going to say secant squared dt, and then we could cancel the dt's out, but then we wouldn't have a dt, and then you can't integrate it. So instead what we'll do is just cancel here and here. That's the same thing. And then we've simplified it quite a bit. Now what I want to do on this thing, just notice we have our bounds going from 0 to pi over 4. I think if we use King's principle here, we can simplify this natural log expression. So just looking at King's principle real quick, what we're going to have is, if we have an integral from a to b of f of x, we can translate this. Of course there's a dx there, and then although we almost canceled it out over there, but anyway. So then for King's principle, if we have this integral, f of x being this right here, we can transform this into f of b plus a minus x. Our a value is going to be 0, b value pi over 4, so for what we're going to need here is going to be f of pi over 4 minus x, or in this case, it's going to be t. So going ahead with this, our bounds are going to stay the same, but then for natural log, we have to input this into tangent. So we're going to end up with tangent pi over 4 minus t plus 1. But now for this right here, we need to simplify this, but we can do that using the different angle formula. For tangent, what we're going to need is tangent of a minus b is going to be the same thing as tan a minus tan b over 1 plus tan a tan b. That's kind of messy. I should do a better job with that. But so anyway, let's just use this formula over here, plugging everything in, because our a value is going to be pi over 4, our b value is going to be t. So looking at this, we're going to end up with tan of pi over 4 minus tan t over 1 plus tan pi over 4 tan of t. Now tan of pi over 4 is just 1, so that's going away there, and that's going away there. So we just have 1 minus tan t over 1 plus tan t. I can take this plus 1. Let's try to combine all this stuff together, because with the plus 1, I can create a common denominator by writing this as 1 plus tan t over just creating a fraction of 1 with the common denominator. But then when we add these two together, the tangents cancel, and then what we're left with here is we're going to have just 2 in the numerator over 1 plus tan t. So then I'll take this and put this back in for all of this here. But what I can do is split this off into two integrals by the properties of the natural log. So the first one, we'll take the numerator. Okay, so I can write this as natural log of 2. And then splitting it up, we need a minus sign, splitting up natural log of division. Create a second integral, 0 to pi over 4. And that's going to be for the natural log of this, natural log of 1 plus tan t. But now here, let's see if we can make sense of all this, because that's just a constant value. So we can easily get a value here. This right here, this whole thing is exactly the same as this right here. Yeah, it's kind of a mess, but anyway, we labeled this I, so this integral here is I. We just changed the order on the 1 plus tan t, but this is identical to this when everything's canceled out. So this here is also I. So then what I can do to clean this up, let's just add an I on both sides. That way we're canceling out this here. We add an I over here. This here is going to become 2I. And so all that's left is we just have to solve this easy integral and solve for I, and then we can finish it off. Okay, now from here what we need to finish it, we just need our I value here. So what I can do to isolate that is let's just divide by 2 on both sides, cancels here. I'll write this as a 1/2 in front right here. We can go ahead and integrate this. This is just going to be 1/2 natural log 2 times x evaluated from 0 to pi over 4. Evaluating at 0 is going to be 0, so we just need to plug in pi over 4 times 1/2. This is going to give me pi over 8 times ln 2. Then we just need to put this back in here and solve this equation that we set up from the beginning. And so what I'm going to do is get a common denominator, because we want 8 on both these. So for this, I'm going to write it as 2 over 8 pi ln 2. And then here we're just subtracting off, like we'll write it as 1 pi over 8 ln 2. Subtract 1 pi from 2 pi, we get our final solution of just pi ln 2 over 8. Okay, there you have it. Really good problem from Vienna Integration Bee 2024. Thanks everyone for watching. Have a good day.